Hello everyone and welcome. In this video we're going to compute the integral from 0 to 1 of x to the negative x dx. So let's denote it by I. Okay, so let's get started. Well, first of all, we're going to rewrite x to the negative x in exponential form. So we're going to rewrite it as exponential of negative x times natural log of x. And of course, this is true because we can write x, the base x, as e to the natural log of x. Okay, so now what we want to do is use a power series. So we're going to use the power series of e to the z, which is given at the sum as k goes from 0 to infinity of z to the k divided by factorial k. So we're going to replace our z by negative x times log of x, times natural log of x. So we're going to get the following integral. Now, the big problem here is whether we can actually move the sum outside of the integral. Well, this is obtained by using the Lebesgue-dominated convergence theorem. Okay, so first of all, we are going to rewrite the infinite sum as the limit of a finite sum. Okay, and then we're going to notice that if you look at the absolute value of the finite sum, well, this is actually bounded above by the infinite sum, which in return is equal to x to the negative x, and x to the negative x can be seen as a continuous function on the closed interval 0 to 1, simply because the limit of x to the negative x as x tends to 0 from the right exists. In fact, it is equal to 1. So we can extend our function by continuity on the closed interval 0 to 1. Okay, so which means we can now apply the dominated convergence theorem. So thanks to the dominated convergence theorem, the limit can go outside of the integral. So the limit goes outside of the integral, and we get the limit as n goes to infinity of the integral from 0 to 1 of a finite sum. Now, we have a finite sum, and we have a definite integral here, or if you want, an improper integral. So simply by linearity of the integral, the sum can go outside of the integral. And we get the following. We also take out the coefficients. Okay, now what we want to do is use the fact that the limit of the finite sum is actually an infinite sum. Okay, so the limit is now equal to the sum as k goes from 0 to infinity of negative 1 to the k divided by factorial k times the integral from 0 to 1 of x to the k times natural log of x to the k dx. Now we're going to call this integral by j of kk. G of kk, where j of k, comma 1 is the integral from 0 to 1 of x to the k times natural log of x to the n dx. Okay, so we're going to compute j of kn. Well, to compute j of kn, we're simply going to use some induction and some integration by parts. So if we integrate by parts, what we get is x to the k plus 1 divided by k plus 1 times natural log of x to the n, which we're going to evaluate between 0 and 1, minus n over k plus 1 times the integral from 0 to 1 of x to the k times natural log of x to the n minus 1 dx. Now, we can see that because of the natural log, if we evaluate the first term at 1, we get 0. And because of the product x to the k plus 1 times natural log of x to the n, if we take the limit, because we can't evaluate it at 0, if we take the limit as x tends to 0 from the right, we we're also going to get 0. So the whole integral reduces to negative n divided by k plus 1 times the integral from 0 to 1 of x to the k times the natural log of x to the n minus 1 dx. Well, this integral is simply j of k comma n minus 1. So by induction, we can say that g of k n is equal to negative n divided by k plus 1 and so on, all the way to negative 1 divided by k plus 1 times g of k comma 0. Well, g of k comma 0 is simply the integral from 0 to 1 of x to the k dx. So it's going to be equal to 1 over k plus 1. Okay? And then we can simply simplify this. We're going to get on top negative 1 to the n times the product from 1 to n, which is simply factorial n, divided by n plus 1 copies of k plus 1. Okay, so we're going to get that j of kn is equal to negative 1 to the n times factorial n divided by k plus 1 to the n plus 1. And then we can deduce g of k comma k is equal to negative 1 to the k times factorial k divided by k plus 1 to the k plus 1. Okay, now we're just going to substitute it in the sum. So we're going to get that I is equal to the sum, as k goes from 0 to infinity, of negative 1 to the k divided by factorial k times negative 1 to the k times factorial k divided by k plus 1 to the k plus 1. Well, we have factorial k divided by factorial k, that's 1. Negative 1 times negative 1 to the k times negative 1 to the k is simply 1 to the k, which is simply 1. So we're going to get the sum, as k goes from 0 to infinity, of 1 over k plus 1 to the k plus 1. Well, by putting n equals k plus 1, we're going to get a sum that will now start at n equals 1. I is equal to the sum, as n goes from 1 to infinity, of 1 over n to the n. Well, this is a series. It's a numerical series, which is convergent. And an approximate value of this sum, we cannot explicitly compute this, but we can find an approximate value, and its approximate value is given by 1.2912. And I think this is a good place to stop. Thank you for watching, and see you next time. Bye.